Okay, so I'm going to go over our ochem 1 review that I gave at the beginning of class. And I'd like to first start by, I'm not going to go over all of these because that's important for you to do on your own. The goal of this is for you to kind of jog your memory and figure out what you remember and what you don't remember from ochem 1. So that's why I included that. And then, I wanted you to build your confidence and start with the questions that you remembered better and the ones that you didn't remember as well. So if you haven't done that, really the most effective way to approach this worksheet is going to be doing that first. So if you've already done that and you just want to see how I work different problems, I'll start going through that now. So we're going to start by looking at functional groups. So primary, secondary, this marker is bad. Oh no. We'll try this one. Primary, secondary, tertiary. For halides, for alcohols are done the same way. So what you'll essentially do is you look at the thing that the halide is attached to, or the alcohol. Look at the carbon that that's attached to, because this can always only be attached to one thing. So you look at the thing that it's attached to, that carbon, and how many carbons is that carbon attached to? So this carbon has 2 attached to it. So this would be a secondary halide. This fluorine is attached to this carbon, 1, 2, 3. So that's a tertiary. So you look at the point of attachment and see how many carbons that is attached to. If you're looking at carbons, you just want to see how many carbons is this carbon attached to. So if it has 4 carbons attached to it, that's quaternary. If it has 3 carbons attached to it, like this one has 1, 2, 3, that would be tertiary. If it has 2, like this one has 1 here, that's secondary. And then if it's at the end, like this one right here, that would be primary. The only thing that's a little different, and it's actually not in this question, is actually for amines. You're not looking for what it's attached to because it can have up to 4 carbons around it, really. You're looking to see the number of carbons that are attached to it. So like this would be a tertiary amine. Or if you have NH2 and then 1 carbon, that would be a primary. So you're looking to see what the carbons are attached to the actual nitrogens. So that one's kind of your exception. But halides, alcohols, and carbons are more similarly counted up. So I'm not going to look at my answer choices. I'm just going to assign these. So this fluorine, this is its point of attachment. That has 1, 2, 3 carbons attached to it. So that's a tertiary. These are all carbons. So I'll just identify this carbon right here has 4. So that's a quaternary. So 1, 2, 3, 4 attached to it. This carbon has 1 on either side. So that's a secondary. And then we have a primary right here. The ones within here are going to be secondary. These are going to be primary. This carbon looks like another quaternary with 1, 2, 3, 4 things attached to it. This looks like a secondary. And then these on the end are primaries. This bromine looks like this is a point of attachment, so that carbon is secondary. This alcohol, that's its point of attachment, that carbon is secondary. And this alcohol's point of attachment has 1 thing, so that's primary. So that's kind of where I start, and then I'll go through and say, do we have a secondary alcohol? Yes, so that's not our answer because we're looking for what groups are not present. Secondary carbon, so there's a secondary carbon there. Primary halide, I actually don't see one of those, so that might be the answer of what's not present. Primary alcohol, we have one right there, and secondary halide, we have one right there. So the answer is answer C. Okay, next question, what functional groups are present? So I'm just going to circle functional groups. So right here we have a ketone, but a lot of times carbonyls can be the basis of other functional groups. So if this carbon was directly bonded to an alcohol, it would be a carboxylic acid, or if it was directly bonded to an oxygen and then another carbon group, R stands for any carbon group, that would be an ester. But it looks like there's 1 carbon separating the other functional groups. So that means these are just separate functional groups. So we have a ketone, and then we have 2 alcohols. Another ketone, and then this we could say is an alkene. I don't know if I would technically call an alkene a functional group, but it's different than just the regular old alkane background. So that's how I'd answer that question. Okay, predict the product of the following curved arrows. So curved arrows, if you remember, They are the movement of electrons. So we would take these electrons, that's where the arrow would start. And if they were moving somewhere else, we would draw the arrow to point there, and that indicates that these electrons are going to leave this carbon and form a bond right here. So I kind of drew it in a different color. Hopefully you can see that. So these electrons, I'll circle them in blue, are going to form a bond right here. They're going to leave the carbon they're placed on and form a bond where the arrow is pointing. So curved arrows are always about bonds forming or bonds breaking. So if we form a bond right there, that looks like this. So this negative charge lost an electron, so it became more positive, and this positive charge gained an electron, and that shared bond right there. So it became more negative, so it was neutral. And if you want to see where those formal charges come from, be sure to add in all your implied hydrogens, and then calculate the formal charge. And you can calculate the formal charge here too. Remember to add in your implied hydrogens, the same ones. And that's where you can see how this becomes neutral. Okay. This one, I actually am going to go ahead and add in the implied hydrogens. There's one right here. There's one right here. Okay. So I'm going to add those in just so we can see as we move forward. What we have here is this lone pair right here is going to form a new bond between the oxygen and this carbon. And then, because that would leave 5 bonds to a carbon, if we just make a new bond, another bond has to break because you can't have 5 bonds to carbon. There's not enough orbitals for that. So this bond would break and form a lone pair right here based on where this arrow is pointing. So I'm going to draw that out. So this is sort of our backbone. These electrons don't move. But the pair that was on top is going to form a new bond right here. That's what that bond is made up of 2 electrons that used to be here. Now this one has broken, and there's going to be a lone pair right there. And we have a hydrogen here, and we have a hydrogen there. And the reason I drew in these hydrogens was so that we could calculate our formal charge more easily, because we've got electrons moving around, the formal charge is probably changing too. So formal charge is valence electrons. So oxygen has 6 valence electrons minus dots minus lines is how some people say it. Others say minus electrons minus bonds. So we have 3 bonds and 2 electrons. So that leaves us with 1. So that's a positive 1, usually just written as a positive. Now over here we have carbon. Carbon starts with 4 valence electrons. It has 1, 2, 3 bonds there, and then 2 electrons. So that's -1, so that would be negative. So our final structure without the implied hydrogens drawn in, hopefully I did too many. There we go. So our final structure would have a lone pair and a negative charge here. It'd have a double bond and a positive charge here. And that would be it. Okay, and these are actually resonance structures of one another because only electrons move, no atoms are moving. And between the two, the more stable one is going to be the larger contributor to the overall resonance hybrid. So that's just extra information, but like this one would be the larger contributor here. And this one, because it's more neutral, would be the larger contributor because more neutral is more stable, and that's better. Okay. Now let's get into acidity. So you can use your pKa table for this. If you've memorized it, that makes it faster, but you can always check that when you're doing your homework. So how I approach this question is first, it's asking for decreasing acidity. So it wants more acidic to less acidic. And I always forget what order the pKa's are in. So then I also remind myself smaller, see I just did it. Smaller pKa is more acidic and the larger pKa is less acidic. So we want the smaller numbers first and the larger numbers last. And then I'll just list out everything and put their pKa. So water is about 15.7. Any alkyne, and this, it'll give you the basic one on the pKa chart, but generally alkynes are going to be in that area, so you can approximate 25. Amines are usually around 38 if they're neutral. And then alkanes, single bond carbon, hydrogen, it's going to be 50. And we're looking specifically at the hydrogens in each of those because acidity is willingness to give up a hydrogen. So that's what we're looking at. So it looks like water, we're already in the right order. Water is 15.7, alkynes are 25, amine is 38, and alkane is 50. So this first one's actually already in the right order. You could double check the other ones just to make sure you didn't make a mistake. But that was handy, so we didn't have to do anything else. The next question is asking us to rank the bold-faced hydrogens from most acidic to least acidic. So again, I always write it out. So larger numbers, less acidic. So it wants us to go from most acidic, which is smaller numbers, to least acidic, which is larger numbers for pKa. I just always have to write that out. Okay, and we're only looking at the bold-faced hydrogen. So again, then you identify what functional group is that a part of. So this is an alkane. This is an alkene. This is a protonated amine. So that means it's going to act differently than the other amines. This is an alkyne. And this is an alcohol. Okay, and I do want to note, so when we think about acidity, we think about if a molecule is willing to give up a hydrogen, and how stable will it be once it gives up the hydrogen? So I'm going to compare the amines and the protonated amines. So if this amine is positive and it loses a hydrogen, it just becomes regular old NH3 with a lone pair because a hydrogen would leave, the proton would leave, and it would keep the electrons on the nitrogen. The hydrogen doesn't take the electrons with it. Now, if this were to lose an electron, it would become NH2, if it was to lose a proton, it would become NH2 with 2 lone pairs on it. So that is going to be much more negative. Nitrogen starts with 5, so 1, 2, 3, 4, 5, 6. That'd be negatively charged, and it would be unhappy. So you're a lot less likely to get this transformation than to get this transformation. From less stable to more stable, or from more stable to less stable. Neutral is better, so we're going from neutral to negative. That's not good. We're going from positive to neutral. That is good. So this is more likely to happen. So this one is going to be more acidic. So actually, the pKa of the protonated amine is closer to 10, while the other amine is closer to 38. Okay, the other ones, nothing too special to note there. We've got 50. Alkene is 25 for a hydrogen off of a carbon-carbon double bond. Carbon off of, that's 45, sorry. Carbon off of a carbon-carbon triple bond is 25, alkyne. And then alcohols are usually in the 16 to 18 range. So I would say that 3 is first, then 4 at 25. Then 5, then 4 at 25. So we've got this one's a pKa of 10, this one's a pKa of 16, this one's 25, and then 45 for the alkene, and then 1 for the alkane. And, if you're doing multiple choice questions and you're not sure of anything other than I'm pretty sure this one, because that's positively charged, is going to be the most acidic, that lets you get rid of 3 answer choices right off the bat, and you're down to a 50-50 chance of getting the answer right. Then they both have the same one for 5, and then now we're looking at the only difference here is between 4 and 2. So if you could just come and look at 4 and 2 and know that an alkyne is more willing to give up a hydrogen than an alkene, then you'd get that question right. Okay, next one, we'll go to resonance. So resonance is something that I see ochem 1 students struggle with more often. Resonance, is in reality, my favorite example is Bruce Banner and the Hulk. There are 2 different versions of one person. Neither of them is the true person. The true person is Dr. Hulk, I think is his name. Dr. Bruce Banner, the Hulk, Dr. Hulk. Or is it Hulk Banner? I don't know. Anyway, that is sort of the same thing with resonance structures, is we have two different structures. Neither of them is true. What's true is kind of like an average of the two of them, right? So we represent them by showing how they interchange between the two. And the biggest thing with these is your electrons move, but your atoms don't move. So already looking at this, I see this hydrogen, it was added to the sulfur and it wasn't there to start with. So this is not a valid resonance structure. The next thing I see is it's asking which one contributes more to the overall hybrid. And typically we want as few negative and positive charges as possible. The more neutral, the better, the more stable. So what I'm seeing here, this one, even if it is a valid resonance structure, is not going to be a good contributor because it has so many negatives and positives. So we can get rid of that. So the only two that I'm really considering are these two. I'm going to check to make sure they're a valid resonance structures each. But typically we want the more negative charge on the more negative atom. So sulfur is more electronegative than carbon. So I'm guessing that 2, if it's a valid resonance structure, is going to be the most stable and therefore the largest contributor. So I've done all that without even drawing one single resonance structure. Now I do want you to practice resonance structures and curved arrows. So I'm going to see if this is a valid resonance structure. So I think that this lone pair would move here. And then if this bond has to break, because that carbon can't have 5 bonds to the carbon, you can draw in all the implied hydrogens if you need to see why that would be true. Then we would get a new bond forming right there and a bond breaking right there. So I'm going to draw that out. So this is sort of our base structure. The lone pairs that were right here are now going to form a bond. So those lone pairs, this arrow is indicating that bond has formed. And then the bond that was here has broken and become an extra lone pair here. And then that would be negative because you took away a bond, but you added 2 electrons. So a negative charge is formed. So that is a valid resonance structure. So this is your answer. Now, it is a worthwhile exercise for you to do the same thing on the other side just to practice your resonance structures. That would be something for you to do in your own time, but to see if this is a valid resonance structure or not. So with the negative charge starting from here, if it would go over to the other side, form a double bond here and make a negative charge there. So is that a valid resonance structure or not? You can check in your own time. It is, but that would be something good for you to practice. Okay, now this says draw the resonance structures of the following molecule. I'm only going to do the major contributors because, again, we could have one that looks like this, but it's not really worth it because it's such a minor contributor. I'm going to start at the most negative place, and I'm going to draw the curved arrows from the negative place to the bond. And you always remember to start your curved arrows at the negative thing, because if I like to think of like negative people would be people who attack others. Positive people aren't really doing that. So if we draw the arrow attacking, or we draw the arrow in the direction of the movement, that should come from a negative place. And then, there's an implied hydrogen here, so we can't have 5 bonds there. So if this lone pair right here becomes a bond, that's not going to be good for this carbon to have 5 bonds. It can't. There's not enough orbitals, so then this breaks and goes right here. So the result of that would be an oxygen here, lone pair. Okay, and then that's become negative charge. And I won't go through the formal charge, but if you're not sure why this is negative, you can calculate the formal charge and see. Okay, and then now this lone pair could come down here. It would form a new bond here, but then there'd be too many bonds to this carbon, so then that double bond would have to break. So then a lone pair would come up here along with a negative charge. This would now be a double bond, and so would that. So these are all the resonance structures that are present. The major resonance structures anyway. If this bond came here, you would have too many bonds to this oxygen, and nothing around the oxygen could break without breaking open the ring. So you can't mess up the basic structure in resonance. All you can do is move the electrons around. So I've moved the electrons around, but the backbone of this hasn't changed. And a good hint to look for things that you could add or break bonds is if there's lone pairs or if there's double bonds. A lot of times double bonds can be broken or lone pairs can become bonds as long as something else can be broken. So that's kind of what you have to look for. Okay, compare the two molecules below. Which is more acidic? Thoroughly explain. Okay, I like to think of acidity as if you lose a hydrogen. So I'm going to draw this hydrogen bond out. So alcohol bonded to a hydrogen, a base comes and it'll take the proton away, but it leaves the electrons behind. So a base is stealing this hydrogen, leaving the electrons behind. Now, the more acidic thing is the thing that can handle the negativity. And just like a friend group, the more support you have to spread around your negativity, the more stable you'll be. So like, imagine you're in a breakup, you can't decide if you want to let this person go or not. If you have friends to help bear the burden, that's going to be better than if you have to bear the burden by yourself, right? Same thing is true with molecules. So if this cyclohexanol lost its hydrogen and it had this negative charge here, now that negative charge is going to be concentrated fully on the oxygen. But the phenol, it has a negative charge too if it loses its hydrogen, but it has resonance where it can spread that negativity around so it's not concentrated in one area. So this could go here and this could break, and then you would get your negative charge right there. Would be a good exercise for you to draw all these resonance structures if that's something that you need practice on. Sorry, it's bad. And then this lone pair goes here and this breaks, and so on and so forth. And it can go all the way around the circle to where you have your negativity spread around a little bit, so it's not concentrated in one area. So because of that, the phenol is going to be more able to handle getting rid of a hydrogen, just like someone with good friends would be able to handle going through a breakup. Okay, which nucleophile would be least effective in an SN2 reaction? A very brief overview of substitution and elimination reactions. Substitution reactions, in both cases, a leaving group leaves and a nucleophile attacks and adds on. The difference is, in an SN1, the leaving group leaves first, leaves behind a positive charge. In SN2, the leaving group leaves as the nucleophile is attacking. I have a lot of videos about this. They're linked at the end of this document, so you can go check those out. Now, the analogy I like to use for this is the bar stool analogy. If you have a strong nucleophile, so you have each leaving group is sitting on a stool, okay? If you have a strong negative person, they will come in and they will push out that leaving group so they can have a seat on this stool. If you have a weak person who maybe is a little bit negative and they want your seat, they won't push you out though. They'll wait for you to leave, and then the weak nucleophile will come in and take that leaving group spot. So stronger nucleophiles tend to an SN2 because they can push the leaving group out, while weaker nucleophiles tend to SN1 because they'll wait for the leaving group to leave. When I say weak and strong, typically we're looking for a negative nucleophile. So all of these are negative. So all of these would probably work in a substitution SN2 reaction. But what we didn't talk about is elimination. In elimination, the mechanism is slightly different, but bigger, bulkier bases in elimination, a leaving group will be a hydrogen will be stolen from the nucleophile that's acting as a base, leaves behind the electrons, and those electrons kick out the leaving group. So when they're bulky, they favor the elimination reaction over the substitution reaction. So that means we're looking for not bulky things to favor substitution, And this is the most narrow, unbranched nucleophile, so it would be the best. So I'm going to draw this whole decision tree out here because the next question is an SN1, SN2. And like I said, I have lots of videos on this if you need it. Okay, sorry, I had to stop to get water. So I have lots of videos on this. If this feels too fast for you, I'm sorry. It's meant to be a quick review. Just jog your memory. If you need to really learn this again, it's probably better for you to go back to those videos. That's why I'm going so fast. But for this one, you want to look at the nucleophile. For substitution versus elimination, you're going to look at the nucleophile. If it's strong, it's going to favor the 2 mechanisms, because in both the 2, the nucleophile acts as the leaving group is leaving. In the weak ones, it's going to favor the 1, so SN1 or E1, where you wait for the leaving group to leave, and then the nucleophile does its job. Once you're in the 2 side, you have to tell if it's going to be SN2 or E2, and E2 is typically favored by heat. And also, because of the mechanism acting as something stealing that bulky base, or stealing from the electrophile and kicking out the leaving group, usually something bulky is going to favor this over substitution, while something narrow is going to favor the substitution if you have no heat. And then if your electrophile is primary, that's better. If your leaving group is primary, it's better for substitution. If it's tertiary, it's better for leave elimination, just because there's all that electron density around it. It's going to be hard for the nucleophile to get in and kick something out, so it'll start to favor E2. I honestly think it's harder between SN1 and E1 because they have that first step of the carbocation forming. These, in reality, if you did an SN1 or an E1 in the organic chemistry lab, you're going to get a mixture of products. But you can, if you use a bulky nucleophile or base and heat, it will favor elimination over substitution, but it's going to be close. But in this case, our nucleophile is terbutoxide. And the way I even know that it's a elimination reaction versus elimination or substitution reaction is because we have a good leaving group and we have this bulky nucleophile. If you weren't sure, you could go through like all the types of reactions you learned in Organic Chemistry 1, just broadly. You learned about substitution and elimination. Those require a leaving group and a nucleophile. You learned about radical reactions. You learned about acid-base, and you learned about additions to alkenes. While there's no good hydrogen here to take for an acid-base reaction, radical reactions require heat or light. And then there's no alkene to add to. So the other thing that you really learned about is a substitution and elimination. And we have all the features for that. Now, when you have a strong base, it's going to go towards SN2 or E2. This is a bulky strong base, so it's going to favor E2. So because we have a bulky strong base, we're going to get elimination, and that means that our base is going to steal, or nucleophile is going to steal a hydrogen, and it can take a hydrogen from either here or here. Now, if you have a more narrow nucleophile with heat that's favoring E2, it's going to take the more substituted, more stable alkene will form from losing the hydrogen that will give you the more substituted, more stable. So that would go here. But because we have a big bulky base, it's actually just going to grab what's easiest on the outside and form the bond right here and kick the leaving group out. So that's known as Zaitsev versus Hoffman, which one it's going to take. This one would give you the Hoffman or the Zaitsev product. It's the more substituted, more stable, and you get it with a smaller nucleophile. So smaller nucleophile gives you a more stable, more substituted alkene. Whereas if you have a big bulky one, it'll do the opposite and give you the less stable. It'll take the easiest one to grab. So that's answer choice E. If you do have Zaitsev product, don't forget that you have to make sure they're anti-periplanar. That requires drawing out, what are those called? Newman projections. Is it Newman? Yeah. And that is probably hard for you to remember, but just a brief overview. Okay, now this is a series of addition reactions to alkenes. The first one is react the molecule with Br2 in heat. So going through everything we learned about, this could be an addition reaction, but usually bromine creates good radicals, and it can create good radicals with heat. So I think it's actually going to add a bromine, and it's going to do it to the most stable position. I'm not going to go through the whole mechanism on this, but that would be the allylic position, one away from the double bond. I'm not going to go through the whole mechanism because this is meant to be a quick overview, but that lets you know you should go back and check radical reactions. The next one, oxymercuration, demercuration. I'm actually just going to draw all three additions of water. So if you have a double bond, you can add water across a double bond. So that means hydrogen on one side and alcohol on the other. So 2 H's and an O, water. Now, the most common that you probably remember is acid catalyzed, where the hydrogen adds first, and it leaves behind a carbocation because the hydrogen adds over here, and it sort of breaks that double bond. And then the alcohol part will go and attack right there. So in that, we get our alcohol adding to the most substituted side because that's where the most stable carbocation is. Oxymercuration, demercuration does the same thing with no opportunity for rearrangement, which we didn't have any rearrangement happening here anyway. And then if we had hydroboration oxidation, it would add, it would add to the other side of that bond. It would add to the top. So our product would look like this. So knowing all those three and how they're different is really valuable. So acid catalyzed hydration adds the alcohol to the more substituted spot where the most stable carbocation is, and that means rearrangement can happen. Oxymercuration, demercuration does a very similar thing, but there's no chance for rearrangement. And then hydroboration oxidation adds it to the less substituted, where the opposite of where it added on the other side of the alkene. So the answer for this one would be this, oxymercuration, demercuration. Oh, look, here we have hydroboration oxidation. Perfect. So I just described why it adds there, but you can go back and review that in chapter 8 in the Solomon's book. I'll have to look at what it is in our new textbook. And then acid catalyzed hydration looks like this. Okay, predict the product if you reacted the molecule with Br2 and CCl4. So that should add 2 bromines across the double bond. And you can again look up the mechanism for that. They're anti to each other. So one's a dash, one's a wedge. And it's, I just lost my train of thought. That goes through the bromonium ion mechanism. And then a halohydrin, I believe, a halohydrate is a bromine on one side and an alcohol on the other. And you would just need Br2 in water instead of CCl4. Okay, so that's the addition of alkene reactions. If you need to review the mechanisms, go back and check that chapter out. Now this is asking how many chiral centers are. So chiral centers where there's 4 different things attached. Right here immediately I see that this has 2 CH3 groups, so that is not a chiral center. This would have 2 hydrogens, so it's not. This has a hydrogen, an applied hydrogen, and then CH2, and then this tertiary, this has CH2, and then a different 2 groups attached to it. So that does have 4 different things attached. I would also say this right here has, is it the same? It's hard to tell because of this right here, but I think this is technically a chiral center because you'd go around. It does have the CH3 on each side, but one's pointing down and one's pointing up. And then I believe this would be a chiral center as well because these are both CH2, but then right here you get to a point of difference. And this would be a chiral center. These are both CH2, and then you get to a point of difference. So I count 1, 2, 3, 4 chiral centers. Hopefully I didn't miss any. I'm tired. Okay, and then last but not least, we have, oh yes, I like this one. So this would be, I can't think of it, chair conformation. So for me, it's easier to see this if I convert it to sort of like a flat ring. And we have axial and then equatorial. So everyone approaches these questions differently, but you just have to see if everything is pointing the same way. So what I see here is both these CH3 groups are pointing up and both these bromines are pointing down. And then one of the alcohols is pointing down and one of them is pointing up. So these, I think, are diastereomers. But I'm going to show you how I convert it. So I always draw out if you have a ring structure with axial and equatorial, and I have a really good tutorial video on this that is way better than what I'm going to do right now. So go check that out if you need to. I believe it's in chapter 4 on my list that's online. But if they were all wedges or if they were all dashes, they would alternate like this. So I'm going to start right here. This OH group is a wedge, and then nothing. So that's up. The equatorial would be the next one up. The axial would be up. The equatorial up. So because this is axial, 1, 2, 3, 4, it is going to be a dash. See, the equatorial there would be the wedge, but this is an equatorial. It's axial pointing down. And then the next one is pointing up equatorial. So that one's also a wedge. So this is what we have on the left side. On the right side, the bromine is pointing down the same way, and the CH3 is pointing up the same way, but the alcohol is actually pointing down. So that has changed. So the only thing that's changed is one stereocenter, so that means it's a diastereomer. So if you're having trouble remembering isomers, we have constitutional isomers and stereoisomers. So constitutional isomers are ones that have like the same basic name, and you have to say cis or trans before them, or R or S before them. Oh no, sorry. Strike what I just said. Constitutional isomers are ones that are built totally differently. So a good example of that is these both have 5 carbons and they both have 12 hydrogens, right? So but they're constructed totally differently. They would have different IUPAC names. But if you have any stereoisomers, they have the same basic name, they have the same basic arrangement, but you'd have to clarify if there's RS or cis or trans. And within these stereoisomers, there's enantiomers, which are non-superimposable mirror images. And then there's diastereomers, which are everything else. So cis-trans falls into that, and if you have only one chiral center different, but the rest are the same, that would also be a diastereomer. So that's how I came to that conclusion. Okay, this was quick, going over everything that we've talked about, or that we did in class. I hope that was helpful to you. If there's anything you need to look up, I have some links for you here. Or you can reach out to me and your PLTL leader and your TAs. Okay, good luck remembering ochem 1.